Hello Chem 212 students, and welcome to our second and final video for this week regarding Chapter 9, Alkynes. When we finished last time, we had talked about the hydrogenation of alkynes and some of the ways in which they're similar to the hydrogenation of alkenes and some of the ways in which they're different. The main one being that when we hydrogenate alkenes, we always get an alkane directly. But if we're hydrogenating an alkyne, if we use a poison catalyst or a dissolved sodium reduction, we can stop and hydrogenate once and make an alkene. Or if we use the hydrogenation, going back here, with a hydrogen with a platinum catalyst, we can hydrogenate all the way from an alkyne to an alkane. Now we're going to talk about it. Hydrohalogenation, which gives us some new things to think about here, because when we're doing hydrohalogenation, we're not adding the same atom twice. We're adding a hydrogen and a halogen atom, so we have to think about regiochemistry and some other considerations that we didn't have when hydrogenating. So in chapter 8 here, the last chapter, we talked about doing hydrohalogenation with an alkene. And when we do this without, as long as we don't use a peroxide, if we just hydrohalogenate with no peroxide, we're going to get the so-called Markovnikov addition here, where the halogen atom will add to the more substituted carbon rather than less substituted carbon. We do have, if we do use the peroxide along with the as a reagent along with the hydrohalide, we can do the anti-Markovnikov addition. When it comes to the addition to the alkyne, here the hydrohalogenation of the alkyne, if we do one addition here, similarly, we'll get a Markovnikov style result where the halogen atom will add to the more substituted carbon, and a hydrogen atom will add to the less substituted carbon, and we'll end up with a double bond here. If we use excess HS, again, we sometimes will say excess or we'll use the abbreviation XS, we can get a dihalide, and so in that case, we get two halogen atoms attached at the more substituted position. And remember, when we have the two halogen atoms here, the two groups attached to the same carbon, we say that they are geminal. So the two halogen atoms here are geminal, attached to the same carbon. So one thing about the mechanism here is, for the mechanisms we've seen so far, they've been relatively similar to those that we learned in Chapter 8 regarding reactions with alkenes. However, the mechanism here, there's some different considerations that we have to think about when considering the mechanism with the reaction with an alkyne. So here, if this mechanism were to occur in exactly the same way as it occurs for an alkene, we'd have the pi electrons here go and do a proton transfer, grab the H+, and then leave those electrons behind on the halide ion, which can then go and attack. And given that this carbon here now has 3 bonds and no lone pairs, it would have a positive formal charge. It would be a carbocation, and this would be if it were behaving, exactly the same way as when we did an alkene. However, that would be a vinylic carbocation, which, as we know from our previous chapters, is not a particularly stable situation. We would prefer to have a tertiary carbocation, much prefer, or even a secondary one. And so this seems like this mechanism would seem to indicate that this reaction would proceed very slowly. But the kinetic data says that it proceeds quite readily. So what's the deal here? It must be, if it's not proceeding slowly, it's probably not going through this vinylic carbocation intermediate, which would be unstable and high in energy and hard to reach. Therefore, you'd end up with probably a high energy transition state and a slow reaction. So when we look at the actual kinetics of this reaction, we see that it's a second order with respect to HX, third order overall. And so the rate is the rate constant times the concentration of the alkyne rather, times the concentration of the hydrohalide squared. Uh, so this is a termolecular type of process. um, so what this means is that there must be two molecules, or it seems to indicate that there must be two molecules of HX, of the hydrohalide, involved in the step of the reaction that's rate determining to produce this. So what might be going on here? So with the transition state, given that we have this overall third order rate, second order with respect to HX, and first order with respect to the alkyne, it must be that the other hydrohalide molecules involved in the transition state, or at least that's one possibility. I think that the details are not completely known, so your book will tell you. It's possible that there are other mechanisms occurring as well. The mechanism isn't completely known, but one possibility is that when the proton transfer is occurring, instead of the proton transfer occurring and getting a positive formal charge here completely, simultaneously we can have the formation, the beginnings of the formation of a bond to the other hydrohalide molecule here. And so there's a transition state involving two of these hydrohalides, both one involving the formation of the bond between one carbon and the hydrogen, the other involving the simultaneous formation of the bond between the carbon and the halogen atom at the more substituted position. So this is a hypothesized mechanism. All mechanisms are hypotheses. This one is less certain, and although it is consistent with the observed rate law, it's possible that there are competing mechanisms occurring, and maybe a little bit of this and a little bit of this, right? But this would be more consistent with the overall rate law, so we give it a little bit more likelihood here. So you may recall that with the introduction of the peroxide, that our hydrohalogenation here proceeded in the anti-Markovnikov process, where the halogen atom is added instead to the less substituted carbon. And this is also true with alkynes. However, it only works with HBr, and this is a radical mechanism as well. So as I mentioned before when we discussed this with alkenes, it's a radical mechanism. We'll talk about the details of the mechanism once we get to the next chapter. But suffice it to say that we will get a similar addition here where we get the halogen atom added. It's going to stop, or we can control it. If we add excess HBr, we can add twice. If we control the amount of HBr, we can add just once here, and the halogen atom will add to the less substituted carbon. We do have stereochemical considerations here. We need to think, well, what side will it add on? And it seems equally likely to add on, or at least somewhat likely, this is a significant likelihood here, of adding in the same side of a large group here like this, in a cis fashion, or on the opposite sides in a trans fashion. So these are two stereochemical isomers that we need to consider when we're doing the hydrohalogenation here. And then one thing to consider as well is that if we use excess of the hydrohalide, we will get a double addition, end up with a dihalide. And of course, we can undo that as we discussed before with our elimination. Again, with the elimination, we need to make sure to use a very strong base, such as sodium, such as the amide ion, sodium amide, the sodium ion being a spectator, the amide ion being the base. And then afterwards, we do have to remember to treat with water to reprotonate the alkyne, because treatment with this very strong base means that the alkyne is deprotonated, and if we want to get a protonated alkyne, we need to add water. And so these are reverses of one, right? The excess HX will do the dihalogenation, and then since these halogen atoms are good leaving groups, we could do a elimination reaction by treating with this strong base, followed by water to reprotonate the deprotonated alkyne that's produced when we use that very strong base. Now, when it comes to the hydration of alkynes, we have a little bit of a different situation that occurs here. So, because when we hydrate the alkyne and add the H2O, we get an OH in the more substituted position. So here, for example, we have acid catalyzed um, hydration here with the H2SO4 in the water. We also have this mercuric sulfate uh, involved as to catalyze the reaction and to make it happen faster, because it does go through, again, just like with the hydrohalogenation, part of the mechanism involves positive formal charge on this carbon, which, again, when we just add once, we end up with a double bond. And so having that positive formal charge in this vinylic position is quite unstable. And so having a catalyst helps us to have this reaction go at a reasonable rate. Now, one thing to consider here is when we're adding, so we're adding, the OH is going to get added right here at the more substituted position with this acid catalyzed hydration. The other hydrogen here is going to go here. And so when it does, we have this vinyl OH group here. And as we're going to see, this will rapidly change into a ketone instead. Essentially, you'll end up with the double bond over here to the oxygen, and this hydrogen will move over to this other carbon. So what's going on here? How come we don't see this addition of the OH to this carbon here, and or at least why doesn't it stay this way? Let's first talk about here the mechanism for this and how the alcohol is produced to begin with. So we use the mercuric sulfate to provide the mercury 2 plus ion here, which will behave as our electrophile. And so we get a nucleophilic attack from these pi electrons here, which are very easy to give away again. And that here makes a bond to the mercury. And then we have this carbon here is now making 3 bonds with no lone pairs, so it has a positive formal charge to it. Then the water will attack where that positive formal charge is, and then since this is a nucleophilic attack from these lone pairs onto this positive area here. Then after that, of course, this is a neutral nucleophile, so we end up with this positive formal charge because this oxygen is making 3 bonds and has 1 lone pair. So before we get a neutral product, this water here, this group, this water that added needs to be deprotonated. So another water molecule comes by, grabs the protons, and then leaves these electrons behind. And now we have an oxygen with 2 bonds and 2 lone pairs. It's neutral. We still have this mercury ion with a positive formal charge on it. And so this is just, re-showing again. This is what we just discussed here, right? The final step here is, remember, this is acid catalyzed here. And so we end up with this intermediate here. This intermediate is unstable if we get this proton transfer. So again, we have these pi electrons here. These can behave as a nucleophile. We have acid. This is this is a reaction here with the acid. We have plenty of acid. And so these electrons go and grab a proton here. And at that point, this hydrogen is going to add right here onto this carbon. And so this carbon now, again, has 3 bonds and no lone pairs. So it's a carbocation. And we have a carbocation that is adjacent to a lone pair here. So we can draw the resonance structure now, where this lone pair now is shown instead as a double bond here. And then finally, we have, since this oxygen is making 3 bonds, double bond here plus a hydrogen, and 1 lone pair, it has a positive formal charge to it. And the result here is that now we can finally lose this bond to the mercury, and these electrons go up. So essentially here we end up with a double bond over here, and we have the alcohol over here. And this is what's referred to as an enol. Enol, meaning this carbon is attached in a double bond. That's where the ene comes from. And this carbon is also attached to an OH group. That's where the ol comes from. Now notice that this is again happening in an acidic environment. And so what we're going to see is that in the acidic or basic environment, these enols are not particularly stable. They're going to undergo what's known as a tautomerization. The enol tautomerizes to a ketone. So tautomerization basically means that you have a movement of atoms within the molecule to produce a new functional group. So we have this enol, but it's in an acidic environment. So again, this is pi electrons here, which can behave as nucleophiles. We've got the acid here. We can end up with a proton transfer. So these electrons here can go and grab this proton. These will end up leaving. These electrons will leave back on the oxygen, and we'll have water that comes out. And at that point, the hydrogen adds right over here. And so again, we've got this carbon with 3 bonds and no lone pairs. And so we again have the situation where we have a lone pair adjacent to a positive formal charge. And so we can have that lone pair move down, and now this carbon is making 4 bonds with no lone pairs. But this oxygen has 3 bonds and 1 lone pair, so it has a positive formal charge. And at that point, we can have the deprotonation here of this oxygen here. It has this positive formal charge, but when the proton is removed, now it has its lone pair back, which came back on the proton transfer, and we have a double bond here. And so essentially what's gone on is this hydrogen that was attached to this oxygen is no longer there. Instead, the oxygen is double bonded to the carbon, and there's no double bond over here now. This hydrogen this hydrogen got taken off, and then a new hydrogen got placed on right over here. So this hydrogen here got placed on right over here, and then afterwards this H plus was taken off. And so the net effect is that the hydrogen moved from being attached to the oxygen to now as the hydrogen attached to the neighboring carbon. And when this occurs, we refer to these as tautomers. They have the same atoms here, just the atoms have kind of moved around during the process, and the ketone being far more stable here than the enol. And equilibrium will favor the ketone quite a lot. And so that's an extra thing to consider in the hydration of alkynes that we did not have to think about in the hydration of alkenes, because when we hydrate the alkenes, we just get an alkane and the reaction is over. We don't have any pi electrons that are going to go and be reactive still, but we know these pi electrons are reactive. They go and do things, right? And so when we have the addition of water and we end up with this enol, the story isn't over. What will happen is that it will be able to rearrange itself to tautomerize and produce the more stable ketone instead. This mechanism is extremely important. You must be able to draw the keto-enol tautomerism. This is going to be important not only in this semester, but in our following semesters as well. Whenever you have an OH, that is basically whenever you have an enol, an OH attached to the same carbon that's double bonded, and you have acid or base in your reaction, you can get this tautomerism that will produce the more stable ketone. Here, when we have a hydroboration-oxidation, so remember the hydroboration-oxidation, which involved the first step with BH3 that in a THF solvent, which keeps it from dimerizing, then a follow-up with hydrogen peroxide and sodium hydroxide. This in the alkenes produce for us the anti-Markovnikov addition of water. And so when we're adding, the water here, the hydrogen ends up at the less substituted position, or the more substituted position rather, and the OH ends up at the less substituted position. So we do get an enol in this case as well, but we don't have an acidic environment this time. This time we have a basic environment, but nevertheless we still get a tautomerization, and because this is a terminal alkene, instead of having a ketone here, we're going to end up with an aldehyde at the end, because right here, there's a hydrogen that isn't drawn. And so when we get the double bond to the oxygen in the end, we have the hydrogen here attached to this carbon, and so we end up with an aldehyde. And so this tautomerization is base catalyzed. So we saw here the acid catalyzed tautomerization mechanism. Now let's look at the base catalyzed tautomerization mechanism. So here we're starting with the enol that was produced after we did the hydroboration oxidation. The OH is attached at the less substituted carbon. The first step here is a deprotonation of this alcohol. So the hydroxyl group here is, we have this is from the NaOH. This can grab a proton and leave this oxygen, leave these lone pairs on the oxygen. And now we have a allylic lone pair. So we can have a resonance here where we end up with the double bond to the oxygen, and then these electrons in the pi bond end up left over on this carbon right here. And at that point, this is very basic. So if we're doing this in water, this is going to go and grab a proton from water and recover our hydroxide ion. So we get a proton transfer. The hydrogen is grabbed here, and the extra electrons are left behind in the oxygen. This gives us back our OH group. And finally, we have the final aldehyde that's produced. This ion right here, when we have the carbanion here, that is right next to the carbonyl, the carbon double bond oxygen, we call that an enolate ion. So that's another bit of terminology. But that enolate ion is very basic. It's going to want, whoops, whoa, what happened? I went far. Okay, sorry. That enolate ion, geez, pressing the wrong button. Okay, that enolate ion here, very basic. It's going to go and grab the proton and leave the electrons behind. We get the aldehyde at the end. So in terms of hydroboration-oxidation, another thing to consider is it does happen in a similar fashion, to some extent, to the alkene. However, if we use BH3, then the alkene can undergo two successive additions, and we may not get the product that we want. And so, practically speaking, when we're doing this synthetically to avoid getting unwanted products, instead of using BH3, what we'll often use is a dialkyl borane. These basically are more sterically hindered. The bulky groups prevent the second addition, so we just get the first and can get the ketone that we're looking for. And so the ones that are commonly used are diisoamyl borane or 9-BBN. This is going to be the one you see a lot. And so this is a reagent, 9-BBN, that's going to be used instead of BH3 for the hydroboration-oxidation of the alkynes as opposed to the alkenes. So here's an example with diisoamyl borane. Again, one thing to think about is you're going to be going through this in your head as you first learn this. You're going to say, oh, okay, I'm doing a hydroboration-oxidation. This means that the OH group is going to attach to the less substituted carbon. So I go from a triple bond to a double bond, and then my OH group is attached over here. But you should be able to recognize, by the way, there's a hydrogen here. You should be able to recognize that this is an enol. So you want to watch out for the enols. So instead of having this, what you're going to have is you're going to have the double bond to the oxygen. And so you get the keto-enol tautomerism. And here, instead of having a hydrogen on the oxygen, you have a double bond to the oxygen. And so this is going to take some getting used to, because it's a bit different. It's a bit different from your hydration of the alkene, because again, it doesn't produce the alcohol. You get the tautomerization, which ultimately produces the aldehyde. So keep in mind, you should never end your product as a enol, right? That's going to tautomerize. So you kind of, when you're thinking about it, even when I think about it, sometimes I go through that step. I say, okay, anti-Markovnikov addition of water. Oh wait, this is an enol. It's going to undergo an enol, keto-enol tautomerism. In this case, it produces an aldehyde, the enol tautomerism. So to summarize, in terms of regiochemistry for hydration and what's produced, if we use the acid catalyzed hydration with the mercuric sulfate catalyst, we're going to get the addition of the OH at the more substituted position, right? So in our brain, we're going through this intermediate where the OH is here, and we get a double bond, right? And so the result is that we now have an enol, and so this is going to tautomerize, where there will no longer be a double bond here. The hydrogen will no longer be here. It will be over here instead, and we'll end up with the double bond to the oxygen. We get a ketone. However, if we're doing a hydroboration oxidation with some substituted borane of some kind followed by H2O2 and NaOH. This is going to go through the enol that has the OH on the less substituted position. But again, we should catch that this is an enol. This is going to undergo tautomerization, so there will not be a double bond here. There will be another hydrogen attached here instead of here, and we'll have a double bond to the oxygen. And remember, since this is terminal, we still have this hydrogen here, which is this one right here. We have an aldehyde. Finally, halogenation. So this one's, again, we have a little bit easier time here with these symmetrical additions. So we're adding halogen atoms. If we halogenate an alkyne and we use excess halogen, excess X2, which is referring here to Cl2 or Br2, and we have a non-polar aprotic solvent rather here. This is tetramethyl or tetrachloromethane. We can add the halogen atoms twice if we use an excess. So we add halogen, 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 right? And so remember that when we were doing halogenation to the alkene, this went through a bromonium ion, or specifically when we were using bromonium ion intermediate. And so that was an important consideration for the mechanism for the halogenation of the double bond. Now, when we use one equivalent, however, we're limiting this to mostly add just 2 halogen atoms, right? And when it comes to how they're added, we're going to get a major product of an anti-addition here. So the halogen atoms are on the opposite sides of the double bond as opposed to the syn addition. Now, remember that if we went on to halogenate the alkene here, if we go on to halogenate the alkene, we're always going to get the anti-addition, because if we're halogenating the alkene, we're going to go through a bromonium intermediate, right? And so then the bromide ion would have to attack from the backside. So if you've forgotten that, I encourage you to go back and understand the halogenation mechanism for the alkene. It's really, really, really important. But this is not an alkene. This is an alkyne. So as opposed to when we're halogenating the alkene, we only really see the anti-addition. Here, the anti-addition will be major, but we'll also get a significant minor component of the syn addition. This mechanism is not completely understood. It's like if it was like the halogenation of the alkene, as I mentioned, it would go through the bromonium intermediate and we'd only get the anti-product. But because alkene mechanism is different, even though we don't completely understand it, we get a significant amount of both products here. Finally, the last reaction we studied in the alkene chapter, and the last one here, or the alkyne chapter, or the last one that's similar to the alkene. It's not the very last one, but the last one that's similar to the alkene chapter is ozonolysis. So in the ozonolysis here, what happened is we chopped up, right? We chopped the double bond. So when we had a double bond, like not triple bond. We had a double bond like this. Let's say we had like this. When we did ozone, what we did was we chopped it in half, chopped the bond in half, and then we made a double bond to oxygen over here, and so we ended up with something like this, and then we made a double bond to oxygen over here, something like this, right? And so we chopped the bond, and we get, for each of those carbons that was involved in the carbon-carbon double bond, they now have a double bond to oxygen. So when it comes to the ozonolysis of an alkyne, it's similar, but instead of just chopping and having the carbon double bond to oxygen like this, we're going to chop, and then the carbon's going to double bond to oxygen, but also we're going to add an OH group to it. So we end up with a carboxylic acid here. So when we chop this one, what we get is we get R1, whatever, this thing attached to carbon, we get double bond to oxygen. So that would be like analogous to what we saw here, the line and then double bond to oxygen. But we have one more thing that we do is we add the OH as well. And we do that on the other side as well. So the ozonolysis here produces, instead of two carbonyls like this, it produces two carboxylic acid groups, one on each of the chopped pieces. And if we do this with a terminal alkyne, then on one side, so we chop this bond, then on this side on the left, we get carbon double bond to oxygen and also bond to OH. But on the right side, it's different, and we end up just with CO2. So that's something to keep in mind as well. Again, the mechanism for this is not completely understood, so you don't need to know a mechanism for this. However, you should be able to use it synthetically to get the carboxylic acid product when you want it. So for example, let's say we're going to predict the products of this reaction. Well, this is symmetrical, so we'll get the same thing twice. But what we're going to get is we got the cyclopentane here, and then we have this carbon. Then we have this carbon that's was on the triple bond. It's going to have a double bond to oxygen and OH. And this is going to be produced twice because it will happen on both sides. So there's the product. Ozonolysis of symmetrical alkynes is very useful to prepare carboxylic acids because you only get one product, so you don't have to worry about separating two different products. If you have a symmetrical alkyne, you'll get all the same product, which is useful when you're just trying to make something and you want it all to be the same and not a mixture of all kinds of different things. And then our last reaction, and sorry, I'm just going to take a look here. Yeah, so our last reaction, and the one that's going to be brand new to us, and the one that's going to be immensely important synthetically, is the one in which we use the alkylate ion as a nucleophile. Okay, and so recall from the beginning of our lecture last time that if we have a sufficiently strong base, such as amide ion or hydride ion, we can deprotonate the alkyne. And so here we have a proton transfer where the proton's being grabbed, electrons are being left behind, and we get that alkylate ion. So those alkylate ions are very nice nucleophiles. And so they can do SN2 reactions. So if we have some alkyl halide, this alkylate ion can behave as a nucleophile, and then we can, for the first time in all of our reactions, this will be the first time where we can add additional carbon atoms to a molecule that already has carbon atoms, as long as it's an alkyl halide or has some kind of good leaving group. It doesn't need to necessarily be a halogen. It could be, for example, cyanide or something that leaves very nicely, right? And so here we have a SN2 type attack here, which will be best, of course, if this is not too substituted, right? But we have the attack of the substrate from the back side here, or in this case, this reagent, and then the leaving of the halogen as a leaving group. And now we have a new CC bond. This is, again, the first reaction that we've learned that allows us to not just move functional groups around or change them, or change a functional group like an alkane into an alkene or something like that. This is the first one that allows us to add additional carbon atoms. And so this is a powerful synthetic tool. So for example, let's say someone, you gave you a synthesis here, and the synthesis has a reagent here, or a substrate that has 1, 2, 3, 4, 5 carbon atoms. But in our product, we want to have 1, 2, 3, 4, 5, 6, 7 carbon atoms. Well, that's telling us that we need to do the reaction that's going to add for us more carbon atoms. And so our reagents here can be, it needs to be the base here, the strong base. Amide ion is a great choice to deprotonate the alkyne, and then some type of hopefully primary alkyl halide, so that we can use the alkylate ion that's produced to do a SN2 reaction and create a new CC bond. So in this, if we're drawing the mechanism for this, we have the NH2 here with a minus charge here. Okay, And we have a deprotonation. So it deprotonates, and that leaves this alkylnide ion. So I'll go draw this on, let's see, over on the side here. So that would produce for us our alkylnide ion. And now if we have this, whoops, erase that real quick. And so now we have this alkyl halide, and so we now have a nucleophilic attack on the alkyl halide SN2, and this goes and hits this guy right here. This leaves, and then we end up with our product here, which has 2 extra carbons attached to that carbon on the triple bond, right? And so you can do this if you have acetylene. You can do this twice, because this works on any terminal alkyne that has a carbon hydrogen bond on the carbon involved in the carbon-carbon triple bond. If you have ethyne or acetylene, you can do this twice because it's got 2 terminal carbons. So here we've added an R group to one side, and then if we do it again, we can add another alkyl group to the side. Notice that this has to happen step by step, which means that we can add. This will end up being somewhat symmetrical in that if we add to one side, it's the same as adding to the other. So we just, for half of our molecules, we're adding an ethyl group, and then after that, if we want to add a methyl group, we can do a second addition. And it doesn't matter which side per se, right? Some of the ethyls are going to this side, some of the ethyls are going to this side. What matters is that one side has ethyl and one side still has hydrogen. And so the side that still has hydrogen, we can add a methyl group to. And so we can make complex molecules that are bigger and bigger by adding additional carbon atoms. And this is our first reaction that allows us to do that. And so this is going to be something you want to keep in mind as you are thinking about synthesis problems. Now, when you see a synthesis problem where you're going to add additional carbon atoms, this is going to be your go-to reaction. We're going to have another reaction like that in Chem 212, and we'll see others in Chem 213. But for now, this is your go-to reaction when you want to make your molecule bigger and have more carbon atoms to it. So finally, what are we going to do for synthesis? So we've been starting to introduce this synthesis, and in each chapter, we're adding more and more reactions, which gives us more and more tools that we can use to synthesize more and more complex molecules. So first of all, if you have an alkyne and you want an alkane, you want to just get rid of the alkyne and make it to a carbon-carbon single bond, well, it's fine to just use H2 with a platinum catalyst, and you're just going to get the alkane. However, if you're trying to get the alkene, you're going to want to use the Lindlar's catalyst, and remember, the Lindlar's catalyst involves a syn addition, same side. So you're going to get the cis type of product here, or you can use a dissolved metal reduction, and you can end up with the anti addition of the hydrogen and get the alkene. And these will both stop at the alkene. And then if you want to go and hydrogenate the alkene, you can do that with hydrogen and platinum. What if you want to reverse the process? So here's where we want to go from triple bond to double bond to single bond. What if we want to go the other way, from single bond to double bond to triple bond? Well, that's nothing new, right? This is a kind of elimination. And so we use a strong base. But our choice of base is going to be important for whether we're going to get a double bond or a triple bond. So here, for example, if we have a double bond and we want to get a triple bond, well, what we can do is we can halogenate it. And remember so this is going to produce for us a vicinal dihalide here, and then we can, if we use excess of the sodium amide and then water to reprotonate, we can end up eliminating twice and getting to the triple bond, right? And so all of these reactions that we've just learned are useful for going between double, single, and triple bonds between carbon all the way through, right? When it comes to going from a triple bond here to a double bond, we use the H2 or Linolaris catalyst. To go double bond to single bond, we can do H2 with platinum. If we want to go from double bond to triple bond, we will want to halogenate the double bond and then use sodium amide as a base to do a double elimination and end up with a single bond here, or the triple bond. When it comes to taking these alkanes, now we know with alkyl halides we can do an elimination with any base and we can get a double bond. But what if here we don't have an alkyl halide? What if we just have an alkane with no halogen atom attached? Notice we don't have any reactions yet that will allow us to add halogen atoms that don't already exist on an alkane, but we will have them. When we get to chapter 10, that's where we're going to get the reactions. So in chapter 10, we're going to get reactions that allow us to go from this to this, let's say. And then once we have that, then we can use a base, right? So then we can use a base. I'm going to make an arrow here like this. If we use some base like NaOH or something, or any base, whatever base, we can do an elimination, right? Like an E2, let's say, and we can end up with the double bond. But we don't have any way to do this yet, this first part. But we will have a way. It's going to be a radical mechanism that will be involved. And so we're going to learn that in chapter 10. So finally, we've gone through a number of reactions as they relate to alkynes. Many of them were repeats of what we saw in chapter 8, right? So we did all of, let's see, these hydrohalogenation, well, not two equivalents, but I guess one. Let me restart that. So we did hydrohalogenation, which there was only one equivalent. When we had an alkene, obviously we can only hydrohalogenate twice. With an alkyne, we can do it, or we can only hydrohalogenate once with an alkene. With an alkyne, we can do it twice because we have two pi bonds. But we did hydrohalogenation, acid catalyzed hydration, Hydroboration-Oxidation, halogenation with one equivalent or two, right? So two equivalents is new. And then ozonolysis. So these were kind of the old reactions right here. Right? I guess we can kind of include these too, but we just did not do them with two equivalents. And so all these reactions are like what we discussed in the last chapter, just a little bit different. The reactions that are new just for alkynes are the alkylation here, dissolving metal reduction, hydrogenation. And we did hydrogenation also in chapter 9, but hydrogenation with a poison catalyst is new. So when it comes to alkynes, we've got a series of new reactions. Again, less so than with the alkenes. Not all the mechanisms are known for these. But for some of them, they are. So, for example, understanding the keto-enol tautomerism, that is super duper important. So when it comes to mechanisms, you definitely want to know the ones for the hydration. So for these, you need to know these mechanisms right here, because these are important. Specifically, you need to be able to describe the keto-enol tautomerism. For these, that's really very, very important. When it comes to the halogenation and the hydrohalogenation, we had some ideas about the mechanism, but they were not completely well known, right? And so you can't really express those mechanisms completely because they're not well known, right? Now, when the other important mechanism that we'll cover more in the next chapter was the dissolved sodium reduction. So we did see that mechanism. It involved a kind of a radical portion to it, and when we get to the next chapter, we're going to be talking about these radicals as well in more detail. We're going to be talking about other radical reactions. In terms of the other mechanisms, for the most part, they were not they were not completely known, right? We did have a mechanism for the elimination here, um, right? But we didn't have a lot of details for any of the others. So for the mechanisms, these mechanisms I presented all the details for, you should understand them. It's helpful because it helps you explain why, right? If you know the mechanism for this one here, you can know why it's a trans addition of the hydrogen anti-addition rather than a syn addition like you would get with just the hydrogenation, the H2 Lindlar's catalyst right here. So that's an important mechanism to know. And here it's important to understand why these don't end up as alcohols, right? They end up as ketones and aldehydes due to the keto-enol tautomerism. So make sure that you understand those mechanisms. All the ones where I said the mechanism is not well known like the rest, you don't need to know the mechanism. But for these ones, you should. So I encourage you to make a note on your reaction list and to kind of go through these and repeat the mechanism a few times to make sure that you understand it. And that'll be it for this week's lectures on Chapter 9. What I want to encourage you to also, try the synthesis problems that I give you in the homework. As we get past Chapter 10, we get to Chapter 11, we're going to have a true focus on synthesis using all the different types of reactions that we've learned thus far. I hope you have a great week, and please let me know if you need any help. Have a good one.